Hello chemists, this is Ms. Placino and you are watching Screencast 3.4 on element families. Today we're going to look at the similarities that elements within the same group exhibit. And really we're going to cover a good chunk of the periodic table, kind of walking through group by group. Again, those are the vertical columns in the periodic table, and discussing both the chemical and physical properties of those elements. There are a ton of really cool videos that go along with this lesson that I didn't include in this PowerPoint. Instead, if you go to the course webpage, they are linked below. I highly recommend that you watch the videos at different points in time during this lesson so that you can follow along with the questions and, if nothing else, just see how these chemicals behave in real life. Let's take a look at the do now. Elements in the same group tend to have very similar properties. Why is this observed? Explain your answer. So pause the video, see if you can come up with a reasonable explanation. Hopefully from the previous unit, you remember that elements in the same group are going to have virtually the same electron configuration. The valence electrons in an element really give it all of its personality, for lack of a better term. It's going to explain why some elements are extremely reactive, while others are relatively inert, which is just another word for non-reactive. If we take a look at group 1, that first column in the periodic table, we'll skip over hydrogen for the time being, but we have lithium, sodium, potassium, and rubidium. All of them have one electron in the s sublevel. The sublevel itself changes from the 2 to the 3, so on and so forth, but it's a very similar configuration: 2s1, 3s1, 4s1, 5s1. And as a result, the elements in the same group, due to the same number of valence electrons, are going to have very similar properties. Let's talk a little bit more about the alkali metals, group 1 elements. All of these metals aren't really what you traditionally think of when you think of metallic elements. They tend to be very soft, and they're also shiny. They're soft enough that you can cut them with something like a knife. Usually when people think about metals, they think of things like iron, for example, which is a very hard, strong metal. That is not the case with alkali metals. These guys react violently with air and water. To the point where they actually look like they're exploding when you throw them in water. And if you react them in the air, if you think about how slowly iron rusts, and that's the reaction of iron with oxygen, it happens almost instantly between our alkali metals and air. Not quite as exciting as the reaction with water, but still pretty impressive nonetheless. Due to this extreme reactivity, we never find group 1 metals, alkali metals, uncombined in nature. They're always present in some compound. And their reactivity is really driven by the fact that there is one valence electron. Now you might be looking at this picture that we've got here and wondering, well, it kind of looks like there's a liquid. What is this stored in? Well, hopefully you know it's not water. This would have exploded if you put all of that metal in water. Instead, your alkali metals are generally stored under oil. Something like kerosene, for example, is a good storing fluid. That way, water isn't going to get in there, because we know that oil and water do not mix, and it's also going to be all but impossible for air to diffuse and react with the sodium that way. So this is typically how we store them. You never want to store them in water. You're going to have an explosion on your hands. It's worth pointing out that these are the most reactive metals in the periodic table. It doesn't get any more reactive than group 1 elements as far as metals are concerned. At this point, you should pause this video and you should watch the alkali metals video that's linked on the webpage so that you can answer these questions. I'm going to make the assumption that you've watched the video, and it is a really fun video, especially as they're throwing all those super reactive alkali metals into water and you're seeing the different explosions. The reason group 1 metals are so reactive is that one valence electron. We know that elements in the S and the P blocks, and I'll just circle them up in the periodic table at the top, are desperately trying to get an electron configuration that looks like a noble gas. If we think about something like sodium, 2-8-1 as an electron configuration, it would do almost anything to get rid of that one electron. That's why it reacts so violently. The reason reactivity changes down the group is because you end up with different distances between the valence electron and the nucleus. So we've got lithium, we've got sodium, and we have potassium. I'll just leave it at those three. In all cases, your valence electron is in the outermost shell, and there's just one of them. As you move down the group from lithium all the way down to, you saw cesium in the video, francium is very rare, so it's highly unlikely that anybody's going to have a video of that exploding in water. Hopefully you realize that those reactions became more and more violent. So when you move down a group, reactivity increases. This can be explained due to first ionization energy and atomic radius. We know when the group 1 metals react, they're going to try to get rid of that valence electron. The farther that valence electron is away from the nucleus, the more loosely it's going to be held. So since it requires less energy to pick that electron off or to ionize that atom and turn it into a cation, it's going to be a more violent reaction. So something like potassium has its valence electron a much greater distance from the nucleus than something like lithium, and for that reason we see potassium reacting much more violently than lithium does. If we move one row to the right, we get to group 2, the alkaline earth metals. Very similar to the alkali metals in appearance, but definitely some major differences in reactivity. These are also fairly soft, shiny metals. They do react with air and water as well, but not nearly as violently as the alkali metals do. Even though they're not as reactive as group 1 metals, they're still not found as free elements often in nature. They're usually combined with something else. And they've got 2 valence electrons that they need to get rid of. So if we think about magnesium, element 12, 2, 8, 2. The reason we see less reactivity from our alkaline earth metals than we do our alkali metals is that it's got to get rid of 2 electrons to get to a noble gas configuration and be stable. So it's going to require more energy to remove 2 electrons from magnesium than it is just going to be to remove 1 electron from sodium. Don't worry, we're not going to go row by row. We'll take out a big chunk of them right now. Groups 3 through 12 are collectively known as the transition metals. And these are traditionally what you think of when you think of metallic elements. They're not very reactive at all, relatively speaking, especially compared to group 1 or group 2 elements. But these are our strong, shiny metals. When you think about things like silver, platinum, gold, not too strong, but definitely shiny, aluminum, iron, things that you've seen in real life. The big thing to know about these types of elements, and I think we touched upon it in screencast 3.1, is that they form very, very brightly colored compounds. You've got all those electrons moving around in the d sublevel, and you can get some really cool colors. Remember, even though they have electrons in the d sublevel, technically the valence electrons are in the s sublevel. We're going to skip over groups 13 through 16. You see metals, nonmetals, and metalloids in those groups. That's right along the staircase. So it's really kind of difficult to classify the properties just kind of based on their group, since you have the 3 different types of elements. So we're going to skip ahead to group 17, which we call the halogens. Halogens are all diatomic. So we have F2, Cl2, Br2, and I2. These guys are super reactive. They will react violently with pretty much any other element on the periodic table, save the noble gases. Those are just really not going to react, especially helium, neon, and argon. In weird cases, you can force something like xenon, Xe, to react with fluorine. Kind of a fun trivia fact, all 3 phases of matter exist at STP. So at standard temperature, which is 0 degrees Celsius, and standard pressure, which is 1 atmosphere, you've got fluorine and chlorine as gases. Bromine is one of the rare liquids on our periodic table, and iodine is a solid. The group 17 elements all have 7 valence electrons. So let's look at something like fluorine, 2-7. We know that fluorine, chlorine, bromine, iodine, any element in the group 17 is going to need to gain an electron so that it can look like a noble gas. It can have a complete octet, which is a very stable configuration. Just like the alkali metals would do almost anything to get rid of that 1 electron, halogens are kind of in that same mode. They're going to do almost anything they can to gain that 1 electron. So as a result, these are our most reactive nonmetals. At this point, I'm going to encourage you again to watch the videos. So pause this one, go back to the web page, pull up the video on the halogens. It's definitely worth your time. It's about, I think, 4 minutes or so, and you get to see some really cool reactions. We can't bring the halogens into school to show you how they react, so this is as close as you're going to get. So the group 17 elements are super reactive, and the reason for that is they only need 1 electron to complete their octet. We've mentioned it a few times. Once an atom has an electron configuration that is isoelectronic to a noble gas, or the same as a noble gas, that's going to be a really stable configuration. Since your halogens all have 7 valence electrons, they're just 1 away from completing that octet, so they're going to react aggressively and violently to try to find that electron. As you move down the group, we saw a general decrease in reactivity. I'm just going to look at fluorine, chlorine, and bromine here. You can imagine iodine is going to have 1 extra energy level compared to bromine. Fluorine is the most reactive nonmetal, and as you move down that group, you still get violent reactions between the halogens and other elements, but nothing is as violent as fluorine. If you think about it, when a halogen reacts, it's trying to gain an electron. And in order to gain an electron, your nucleus has to be able to pull an electron towards itself. I'm going to draw in that extra electron that the halogens are so desperately seeking. Hopefully you recognize, you can see that as you move down the group, the distance between where that extra valence electron would go and the nucleus is getting larger. As the atom becomes larger, the nucleus has a weaker grasp on those outermost electrons, and it's going to be more difficult for them to attract an electron to itself. So the key to fluorine's reactivity really stems from the fact that it is a small atom with a strong nucleus. You might be thinking, well, wait, fluorine is element 9, chlorine is element 17, so there are 17 protons in fluorine's nucleus. Don't forget, there's also that extra energy level, so even though the nucleus is technically more positive, because you've got all those electrons to keep track of and a whole extra energy level to put them, the overall effect is that chlorine is not going to be able to pull the electrons as closely as fluorine can, and therefore is less reactive. Last but certainly not least are the group 18 elements, the noble gases. The noble gases were some of the last elements to be discovered due to their highly unreactive nature. A lot of times you might read that they are inert. Inert's just a fancy word for non-reactive. As the name suggests, all of the group 18 elements are gases at standard temperature and pressure. You can make it cool enough where you can get them to liquefy. These guys do not react under normal circumstances. Again, something like helium, neon, and argon, you're just not going to get to react at all. Something like krypton or xenon, you might be able to get it to react with fluorine. But remember, fluorine is the most reactive nonmetal on the periodic table. Their stability stems from the fact that they have a complete octet of electrons in their valence shell. They've got 8 valence electrons, and as a result, it's not in their best interest to either gain or lose electrons, so they tend not to interact with the other elements. That's part of the reason they call them the noble gases. Just like nobility, like kings and queens and stuff like that, are too good to interact with the common people, the noble gases kind of take on that same snooty behavior. They've got nothing to gain from interacting with the rest of the periodic table, so they largely just kind of do their own thing and don't react with anything. Hopefully you're getting the idea that these are the least reactive elements on the periodic table. There's a section in your workbook that addresses what you think the most reactive metal and most reactive nonmetal is, along with some space to explain why. There's also a video back on the web page that shows the reaction between sodium and chlorine, and if you watch it, you'll see that it's a violent reaction. So please pause the video, watch the reaction between sodium and chlorine, it's about a minute or so, and think a little bit about what the most reactive metal and nonmetal may be. Let's take a look at this. The most reactive metal. Well, hopefully right off the bat you are thinking group 1 metal. It's got to be one of the alkali metals. We know that the reactivity increases as you go down the group, as that valence electron gets further and further away. So if you said that the most reactive metal is francium, or technically cesium, we're going to take that as a correct answer. Again, francium is super, super rare. I think they estimate that at any point in time on Earth, there's like less than 100 grams of francium available. So it's kind of a ghost, really. Certain atoms will decay into it, but it also decays, so we don't have much of it at all. Cesium is also relatively not abundant, but it is definitely more so than francium. So usually I'll tell you that cesium is our most reactive metal, and it's because it's able to lose that one valence electron really easily. I'm going to circle cesium on our little periodic table. I guess I'll just fill in the dot. The most reactive nonmetal. Well, let's throw out the group 18 elements, our noble gases, right away. We know they don't react with much of anything. Metals and nonmetals have opposite tendencies and behaviors, so you probably want to pick something as far away from cesium as you possibly can. It's going to leave you with fluorine. Fluorine is our most reactive nonmetal. It's really driven by the fact that fluorine is a small atom with a powerful nucleus that is really, really good at attracting electrons towards itself. Cesium is great at becoming a cation and getting rid of its electron. That's why it's our most reactive metal. Fluorine is excellent at becoming an anion. It's like an electron hoarder. If it can find one, it'll take it. It can get it from pretty much any element on the periodic table that it wants. So its reactivity is driven by the fact that it is small and has a high, or I guess I should say a very negative electron affinity and a strong or high electronegativity. The reaction between a group 1 and group 17 element is really like a match made in heaven. You've got something like sodium in the video, which we know really, really wants to lose an electron and become a sodium plus ion. And then you've got chlorine, which really wants to gain an electron, minuses in there, and become the chloride anion. So this is a win-win situation. Sodium's got an electron it doesn't want. Chlorine is on the hunt for an electron. So immediately, these two things are going to react, and because both of them are now achieving a stable octet from 2-8, 1 to 2-8, and from 2-8-7 to 2-8-8, we are going to see a ton of energy being released. We know that complete octets, 8 electrons in the valence shell of our group S and p block elements, leads to stability. Stability is attained by releasing energy. So when I take a group 1 metal that wants to give up an electron and a halogen that wants to gain an electron, and I allow them to react, you're going to see a very, very violent reaction. We can wrap up with a 60-second summary, so take a minute or so to write a few sentences summarizing today's lesson. If I were you, I'd really focus in on that connection between valence electrons and reactivity. If you haven't done so already, go ahead and watch those videos. They're really fun. They show demonstrations that I can't do in school for safety reasons, and it's definitely worth the 10 minutes or so it would take you to watch them. I hope you found this video helpful, and we'll talk again soon.